This is, all right, this is Friday, November 13th, 2020, which means it's now 8 full months since the school has shut down in-person instruction on campus. This is Physics CP, a debrief on inelastic and elastic collisions in one dimension, problem number 4, which is extremely challenging mathematically. Problem number 4 reads, two balls collide in a head-on elastic collision and rebound in opposite directions. One ball has a velocity of 1.2 meters per second before the collision and negative 2.3 meters per second after the collision. The other ball has a mass of 1.1 kilograms and a velocity of negative 4.2 meters per second before the collision. That's all they give us. So we're missing the mass of the first ball, which I'll use the variable m to represent, and we're missing the final velocity of the second ball after the collision, and I'll represent that with just v for velocity. If I wanted to get fancy, I would give it a subscript b final, but it's the only unknown velocity, so I'm just going to call it v. So here's a crude sketch of the problem, and they ask in part A, what's the mass, and in part B, what's the velocity of the second ball after the collision. To solve this mathematically, we have two tools to use. The first one is conservation of momentum. The sum of the total momentum before they collide has to be equal to the sum of all the momentum after they bounce off of each other. And momentum for one object is the product of mass times velocity for that one object. By itself, this is not going to solve the problem. In addition to momentum, it says this problem is a head-on elastic collision. So we can bring to bear conservation of kinetic energy, which states in a perfectly elastic collision, and it doesn't have to be one-dimensional, it can be multi-dimensional. In a perfectly elastic collision, the sum of the kinetic energy of all the objects before they collide is equal to the sum of all the kinetic energies after they bounce off each other. And the formula for kinetic energy for any one object is 1/2 times the mass of that object times its velocity squared. Momentum is a vector. It's a magnitude with a direction. So I can even put little arrows above its symbol to remind you that if this is going east, that is going east. If this is going at 45 degrees above the horizontal, this must be going exactly the same direction as well. Kinetic energy is a scalar, and by the way, it can never be negative. Even if the velocity is negative, after it's squared, it becomes a positive number. Mass can never be negative. 1/2 is a positive number. So kinetic energy, at its very least, is 0, and it's a positive quantity greater than 0 if a non-zero mass is moving with any velocity at all. All right, so these are the two math tools I have for this problem. Let's apply them. First, I'll do conservation of momentum for this collision. Before they collide, the left mass is going at 1.2 meters per second. Now, as a good physics teacher, I should always write all the units with every variable. But I want you to see the naked math and not get lost with the units obscuring your view of the math relationships. So I'm going to write it without the units and say, look, mass times velocity before they collide is going to be 1.2 m. Mass, velocity, 1.2 m. That's for the left guy. For the right guy, he's going to the left. That makes it a negative quantity. So minus 1.1 times 4.2 mass times velocity in the negative direction. This is before they collide with each other. It must be set equal to the total momentum after they bounce off of each other. After they bounce, we have negative 2.3 times m. So I'm going to write minus 2.3 m mass times velocity in the negative direction. And for the right guy, we're going to presume he bounces to the right. If we're wrong, that will show up as a minus sign later on. So it's okay if, if we're not sure. But we have mass times velocity. So plus 1.1 times v, the unknown final velocity of this second mass. Meanwhile, I'm trying to maneuver to where I can actually see my students while I teach. Takes a minute. All right, what I can do is fire up my calculator. Which I don't even see right now. I'm going to pause. Boop. So, kids, you're going to have to do the math for me. I'm going to add 2.3 times m to both sides of this equation. So I'm combining like terms. Now this one I can pretty much handle. 2 plus 3 is 5. 2 plus 1 is 3. So I have 3.5 m on the left. Calculate, please, what is 1.1 times 4.2? Oh man, should I call on someone? Oh yeah, hey, stand by another moment. Fabian, what is 1.1 times 4.2? Thank you. So based on conservation of momentum, at the moment, I have 3.5 times m minus 4.62 equals 1.1 times v. Now, I want to take some time mathematically and remind you that this is a linear equation. Linear, just like you learned in math class. In math class, you used to have something that looked like y equals mx plus b, where m was the slope. By the way, don't mix up this slope from math class with this mass from physics class. These are two different m's here. Don't mix them up. And then b, you call that thing the y-intercept. And if it had a positive slope and a positive intercept, then it would look something like this when you plot it on a Cartesian coordinate system of x and y. Great. So now I want to prove to you that, yeah, this is that relationship. And sadly, I forget which way I'm going to do this. I think I will make v, so I'm going to say let x equal v, let y equal m. That might be backwards. If it is, I'd have to do it again. So let's see, that makes this thing look like 3.5 times y. I'm going to add the 4.62 to both sides. So this becomes 1.1 times x plus 4.62. There. I've rearranged the equation to make it look much more like y equals mx plus b from math class. Of course, if I want to make it look even closer, I should go ahead and divide both sides by 3.5. All right, fire up your calculator. By the way, I can put this into my calculator without, oh, actually I can't because I need my graphing calculator to actually show you the results of graphing this. I guess I could use Desmos, or I can just do it this way. Kids, open parentheses, 1.1 times x plus 4.62, close parentheses, divide by 3.5, and I claim this is the equation of a straight line with a y-intercept a little bit greater than 1 and a slope of about 1/4 or so. If you happen to have a graphing calculator, take a moment right now and enter this in. So if you have a TI model, for example, it would be the y equals button, clear any previous equations, enter, you can do it this way, open parentheses, 1.1, find the button labeled x, t, theta, whatever it says, plus 4.62, close parentheses, divide by 3.5, enter. Then go over to the window button maybe, and select standard so that it will graph it for you. And you should get something that looks like this on your display. Sadly, I don't see my calculator yet, so you do it. Oh, drats. I can't even join. Okay, I'm joining my own classroom so I can finally see you. All right. Let's. How annoying. Zara, were you successful in doing this? Okay, I'm going to move on. So by ourselves, we have two unknowns here, and I can't tell you where we are on this line, but our solution is somewhere along this line. This is based on conservation of momentum. Now, let's bring out the second tool, the tool that says use the principle of conservation of kinetic energy. All right, so before they collide, I have 1/2 times mass. I don't know its value, and this is not slope, this is mass. It's initial velocity was 1.2. So I'm going to square that. For the second object, it's 1/2 times 1.1 kilograms times negative 4.2 squared. This is the total kinetic energy before they collide. I set that equal to the sum of the kinetic energy after they bounce. So for the first guy, that becomes 1/2 times m times negative 2.3 squared plus 1/2 times 1.1 times v final squared. Oh my goodness. You know me, I do not like having a 1/2 everywhere. And if it's everywhere, I just multiply by 2 and get rid of it everywhere. Now I need your help. Random volunteer, what is 1.2 squared? Ray. All right, so this first term becomes 1.44 times m. The second term, kinetic energy is always positive. Calculate, please, someone. What is 1.1 times 4.2 squared? 1.1 times 4.2 squared. Nathan, H. I thought it was 19.404. Is that correct? Oh, okay. Yeah. Yeah, I'm carrying it farther out than I should have. So that's the kinetic energy from the second ball before they collide. Now I set that equal to the kinetic energies of the two objects after they bounce. Volunteer, what is 2.3 squared? Tony. Yep, that is the first term after they bounce. So it's 5.29 times m. This last term is plus 1.1 v squared. This is from conservation of kinetic energy. I would like to combine like terms and simplify. I would subtract 1.44 m from both sides. That means this thing becomes 12 minus 4 is 8, 4 minus 1 is 3. I get 3.85 times m plus 1.1 v squared is equal to 19.404. Great. Does anyone recognize what kind of shape that one is? Yes, yeah, it is. If I let x be equal to v and y be equal to m, this thing would look like 19.404 is equal to 3.85 times y plus 1.1 times x squared. I could subtract 1.1 x squared from both sides. 3.85 times y would be equal to negative 1.1 x squared plus 19.404. After I divide both sides by 3.85, page 2, oh man, November 13th, 2020, page 1. November 13th, 2020, page 2. Don't throw it away, Mr. Turk. Okay, this thing looks like y equals, open parentheses, negative 1.1 x squared plus 19.404, close parentheses, divided by 3.85. This is y equals ax squared plus b, a parabola. A is negative, so this is a downward opening parabola. It does go above the x-axis. If I were to graph it, oh man, go ahead. If you have a graphing calculator, put this in as the second equation. Open parentheses, minus 1.1 x, the x, y, or x, t, theta, n button, x squared button, plus 19.404, close parentheses, divide by 3.85, enter, graph. Tyler, that does look disgusting, but okay. What you should see on your graphing calculator should look like that. Does anyone have it where they can share with us? No, because you'd have to hold it up to your screen. Okay, can anyone hold up their graphing calculator display to the screen? Oh man, there's our 3-minute break. Yeah, okay, and your contrast isn't good enough for it to be displayed. All right, take a 3-minute break, everyone. All right, so, in our last episode, we left off with the equation of a parabola and separately the equation of a straight line. I'm going to write them both again so you can see them one right next to the other. So for one, we have y is equal to, open parentheses, 1.1 times x plus 4.62, close parentheses, divide by 3.5. This is based on conservation of momentum. And this other one, y equals, open parentheses, negative 1.1 x squared plus 19.404, close parentheses, divide by 3.85. This was from conservation of kinetic energy. I have two equations, two unknowns. Graphically, you can see there are two intersections. Those two intersections are the two solutions. if you have put this into your graphing, okay, what if you don't have a graphing calculator? In that case, I would say you have to actually get rid of the parentheses and then substitute for, no, actually, here's what I would say. Look at this. If y is equal to this from conservation of momentum, and y is also equal to that from conservation of kinetic energy, then this is equal to that. Mathematically, that means 1.1 times x plus 4.62 close parentheses divided by 3.5 is equal to open parentheses negative 1.1 x squared plus 19.404 close parentheses divided by 3.85. What is that, you ask? Well, I claim, when you distribute the numbers, get rid of the parentheses, then combine like terms and simplify it, this will become ax squared plus bx plus c when you rearrange it into standard form. That's wonderful. That means you can solve it by factoring, which is not going to work because that's too hard. You can solve it by completing the square. Best of all, you can solve it using the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Yes, you get to use something from math class here in physics class. This will work. It will give you two roots. One of the two roots, I believe, will be for mass equals 0. Okay, I think this guy intersects at mass equals 0, which is crazy, right? I think the velocity would be negative 4.2 meters per second, and the mass is 0, and that would be a solution. But for us, we don't want m equals 0 as our solution. Eating in class, Tyler, as you drive ever farther away from class? Yeah, all right. Oh, where's your napkin, child? Where's your napkin? Okay. We want this solution. And I challenge you students who put this into the graphing calculator to go get this solution using your TI technology. So what you should do is go and select Calc. Select Intercept. It will then ask you, is this curve 1? And you would say, yes, that's curve 1. And then it'll ask you, is this curve 2? And you would say, yes, this is curve 2. And then it would ask you, guess where the solution is that you want. That is when you move your cursor to this intersection. Then when your cursor is around there, doesn't have to be exact, but you're telling it it's not that solution, it's this solution. So once you move your cursor around here, press the enter key, and it goes doo, 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 doo. Sound effects added just for the pleasure of it. And I'm curious if I randomly call on you, Tenrusi, are you able to do this? Do you have a TI? Did you solve it? Oh, child. I could do that as well, but I'm too lazy to do it. Should I wait for you? You're muted. Oh, I hate that answer. You know that cost you points, right? I'll give you another 30 seconds. All right, here we are 30 seconds later. How you doing? Okay, I'm gonna then move on and ask Augustine, were you able to do this? Do you have an intersection? 3.1 for x and y equals 2.94 is correct. Okay, now, oh, right. 2.294 for y. All right, now I'm going to try to prove to you that that is correct. Our little code said we let x represent the velocity. So 3.1 should represent the final velocity of the 1.1 kilogram mass. And y should represent the unknown mass, 2.294 kilograms. Now, how do we get any confidence that these are the actual correct numbers? The answer is you should plug these in to the momentum equation. That's the one I would do. The momentum equation said 1.2 times the original unknown mass minus 1.1 times 4.2 is equal to negative 2.3 times the original mass plus 1.1 times the final velocity. So, in fact, we can take it to this point. 3.5 times the mass minus 4.62 equals question mark 1.1 times the final velocity. All right, so let's do that one. 3.5 times 2.294 minus 4.62. Okay, someone calculate that much. What is 3.5 times 2.294? Then subtract 4.62, enter. Random volunteer, Joseph. Okay, now it's 1 second later. What do you get? Harshis, do you agree with that? I'm going to write it down. 3 point, repeat. Interesting. So this is the momentum before using those values. Now let's compare that with the momentum after, which is negative 2.3 times 2.294 plus 1.1 times 3.1. All right, volunteer, what do you get? What is negative 2.3 times 2.294 plus 1.1 times 3.1? Siddharth. Interesting. And Jonathan, do you agree with that? Well, in my head, negative 2 times 2 is negative 4. 1 times 3 is 3. Negative 4 plus 3 is indeed a negative number. So I kind of like that answer. What was it? Negative 1.866 kilogram meters per second after. So there's two possibilities here. One, we don't have the right answer. Two, you guys goofed your math. 3.5 times 2 is around 7. 7 minus 5 is around 2. I think I'm doing this incorrectly. Yeah, I am confident that these are the correct answers. I also believe, looking at my earlier notes, that I'm doing the check incorrectly. So let's do the check this way instead of here where I goofed. Okay, we just did negative 2.3 times 2.294 plus 1.1 times 3.1. And we get this. What we should do as our check is this, not this. Okay, so instead of doing this, calculate please, what is 1.2 times 2.294 minus 1.1 times 4.2. That is what we should have done. Okay, do this calculation. 1.2 times 2.294 minus 1.1 times 4.2. Tyler, are you able to do it? This looks like it's around 3 minus more than 4. So yes, this should be a negative result. What'd you get? 1.8672. Okay, kids, look, to better than 3 sig figs, they're identical. So we got the right solution. In summary, the mass was 2.29 kilograms. I'm rounding a little bit. And in part B, the final velocity was 3.1 meters per second. Ta-da! We just spent most of an entire period debriefing on one math problem, one physics problem. This is slightly more involved than what is expected of you students these days. All right, now that we've solved the problem number 4, I do want to take a moment and remind you students about the units, the variables that we use here in this course. So for distance, we use the variable called x, and its unit is in meters. Okay, so this m means meters. We really have 3 meanings for m, right? We use it for meters, we use it for mass. Okay, two meanings. We use for speed or velocity, we use v, and those units are meters per second. For acceleration, the variable is lowercase letter a, and we use meters per second squared. For force, we use capital F, and those units are kilograms, meters per second squared, which we also call a Newton. So a Newton is a kilogram meter per second squared. We also have energy, capital E, or work, capital W. Those units are kilograms meters squared per second squared. So we can call those things Newton's meters, or we can call them joules. And the newest addition to our list, momentum, lowercase letter p, those are kilogram meters per second. And there's no other name for them. They're always called kilogram meters per second. Live with it. I guess I can add to this list, which I didn't do before, and say impulse we use Newton seconds. And sometimes we use, I think, capital letter I for that. But that's something I didn't share with you before. So for impulse, they sometimes use capital letter I, and its units are newtons times seconds, because force times change in time is newtons times seconds. Okay, so in this problem, we have a golf ball. Its mass is 200 grams, which makes it 0.2 kilograms. I thwack it. It goes at 14.8 meters per second. So its impulse is 2.96 kilogram meters per second. If I were to ask you if the time that I spent hitting the golf ball is, yikes, I need some small integer, Matthew B. Give me some small integer. So you don't know what an integer is very well. Like a whole number? Can you give me a different whole number? Can you give me a different whole number? No, no, not 0. Uh, just go a little bit higher, please. Okay. So let's say the time is 3 milliseconds. Milliseconds. I remind you, this is a Greek prefix that means 3 times 10 to the negative third power seconds. So calculate, please, if the impulse is 2.96 kilogram meters per second, and the time that the club spends hitting the ball is 3 milliseconds, what is the average force of the club hitting the ball? What is F? If F delta T equals 2.96. Calculate, please. And someone hold up your hand if you have the answer. Okay, let's go with Jacob. What do you get? 990 newtons, child. 990 newtons. Anyone disagree with that? Nope. Okay. So this is an example of your homework assignment. By the way, which is greater? Last question. The force of the club on the ball or the force of the ball on the club? Jacob, what do you say? And Zara, do you agree with that? Okay, you're both wrong. By Newton's third law, they're equal and opposite in magnitude. Opposite in direction, equal in magnitude. So the force of the club on the ball is equal in magnitude and in time duration to the force of the ball on the club. This concludes today's